We now turn to the study of galaxy formation for stars, galaxies, and the cosmic reionization. This is probably the most active area of observational cosmology today. First, some preliminaries. What do you mean by galaxy formation? Galaxies kind of keep forming all the time. There is no really sharp definition between formation and evolution. And just as with galaxy evolution, there are two components to it. How do you assemble mass, and how do you turn gas into stars, and then their effects on the remaining gas? Obviously, galaxy formation as well as the evolution have to be related to their large-scale environment, as they are sort of low-end extension of it. But unlike structure formation itself, galaxy formation includes very dissipative processes, in particular star formation. We now also know that processes of galaxy formation seem to be somehow closely coupled to the formation of the central supermassive black holes, and we'll address that in a little more detail later. But generally, when people talk about galaxy formation, they usually mean assembly of large galaxies of today somewhere at large redshifts, certainly greater than 3 or 4, maybe greater than 5 or 10. Little dwarf galaxies may be just coming together today, and so we do see some residual galaxy formation going on. So over the last decade or so, we discovered large populations of young galaxies at large redshifts, young simply because the universe was young then, and now we have a fairly good idea of how the whole process works. And indeed, you can think of the frontier as understanding the very first star formation and formation of first protogalactic fragments and how they reionize the neutral universe somewhere around redshifts between 6 and maybe 15 or 20. To recap the general picture of structure formation, we start with small initial density perturbations that come out of the Big Bang. They keep collapsing, driven by the dark matter, and that process begins well before recombination when microwave background is released. At that point, there are no sources of light in the universe for a while, and baryons, gas, keeps falling into the potential wells delineated by the dark matter. At some point, the very first stars begin to form. That probably happens around redshifts of 20 or 30 or so, but nobody really knows for sure. By a redshift of 6 or so, the young stars from freshly formed protogalaxies or their fragments reionize the universe, and it becomes transparent to UV radiation again. All through this process and continuing to the present day, there is a hierarchical structure formation that galaxies merge or smaller fragments are absorbed into the large ones. So the galaxy growth continues. As far as stellar populations are concerned, massive stars will produce heavier chemical elements in their cores, explode the supernovae, return them to the interstellar medium from which new stars are formed, and so on. And in this way, we have ever more chemically enriched interstellar material as well as new generations of stars. An important player in all this may be energetics related to supermassive black holes in galaxies, those responsible for quasar-like activity, because they can dump substantial amounts of kinetic and radiative energy in their hosts and modify their evolution as well. So here is a nice schematic illustration of the early cosmic history. This one is due to Avi Loeb. In the beginning of this particular segment, we have cosmic microwave background recombination, at which point the universe enters what we now call dark ages because there are no sources of light. Dark hills keep collapsing and eventually ignite some star formation, and more of those happen. When the ionized bubbles of gas around those first protogalaxies start to overlap, this is what we call the reionization era, or the universe which was filled with neutral hydrogen and helium ever since the microwave background was released, now becomes ionized again. And that is probably as good boundary as any when we say, well, this is roughly where galaxy formation is really occurring. And after that, obviously, evolution of galaxies continues. So the assembly of the mass is driven by the dark matter, and those potential wells keep us getting assembled through accretion of more material. A way to characterize them is by their mass function, how many there are at any given mass. Here is a set of theoretical curves of how the mass function of dark halos evolves as a function of time. There are many small ones and there are a few large ones, but if you look at curves which are labeled by the redshift, early on at high redshifts there are really very few very massive halos, and the growth keeps occurring. There isn't so much growth at low mass end, but you start populating the high mass end with ever more massive halos, and that process continues until today. So one of the important predictions of our general theoretical understanding of structure formation is that there will be relatively few massive potential wells, massive galaxies early on. While we discussed structure formation, we talked about essentially gravitational processes. Galaxies follow that as well, but there are also much messier dissipative processes. But gas is converted into stars, stars radiate energy, change to gas, stars explode, and so on and so forth. These processes are impossible to model analytically, not because they're hard, they truly are impossible to model analytically, and they can be only studied numerically. So we do not have a clean-cut theory of star formation, although we do understand it fairly well in some sense. And that then maps into our relatively shaky understanding of how initial star formation proceeds. Nevertheless, much progress was made, and we'll talk more about that later. So all of the things that I already mentioned are parts of the overall picture of galaxy formation and evolution. But the basic paradigm is very simple. You have potential wells formed by dark matter, which can keep merging, and they form containers for the gas that will fall in, get sufficiently dense in the middle, that will start making stars. So generically, we expect that dark halos will be more extended than the stellar components of galaxies, which was exactly what we've seen when we discussed global properties and structure of galaxies. So for a while, proto-galaxies, or really young galaxies, were something of a mythical creature, and the question is, how do you define one? And there are many different ways in which you can define it as some first X years or a fraction of the age of the galaxy's life, or when a certain fraction of the mass is assembled, a certain amount of stars is assembled, and so on. Or you can simply declare that beyond certain redshift, everything should be treated as a young galaxy. It doesn't really matter. Essentially, we try to map the whole process from the very first star formation until galaxy evolution to the present day. But for a variety of reasons, we think that in most young galaxies there was very intense star formation, and there should be very luminous objects because of that. Although obviously there'll be a lot of small ones and very few really massive ones early on. So it's the energy release from forming galaxies that makes it possible for us to see them. And there are essentially two major mechanisms for young galaxies to create energy. First of all, it's their collapse from large-scale structure. You recall that cooling plays a crucial role, that galaxies are 1,000 times denser than they should be if they're just extrapolation of large-scale structure. That is, they collapse by an extra factor of 10. And therefore, binding energy change due to the dissipative collapse overwhelms any changes in binding energy from simple gravitational collapse. However that happened, half the potential energy today is equal to the kinetic energy in galaxies within a sign, and therefore we can estimate kinetic energy of a galaxy today, and this much energy was also released in process of proto-galaxy collapse. So we can take approximately mass of the cooling materials, that will be the baryons, and multiply it with a square of characteristic 3D velocities in galaxies. And so for typical numbers that are relevant here for galaxies, say like the Milky Way, the relevant number is roughly 10 to the 59 ergs. That's just for the baryons, part that cools. There's 10 times that much in dark matter, but there is no visible signal from its assembly or collapse. And that sounds like a lot of energy. Turns out actually that conversion of gas, interstellar material, into stars also produces additional amount of energy, which is approximately of the same order. So just putting things together will release of the order of 10 to the 59 or a few times 10 to the 59 at most of energy. But it's not the energy that matters, but luminosity, or what time interval this has been done. However, the second source of energy is actually more important. And this is conversion of hydrogen into helium in massive stars. The thermonuclear fusion in stars, converting hydrogen into helium and then heavier elements, releases energy, and approximately 0.1% of the initial mass of hydrogen is converted into energy. It turns out that subsequent fusion from helium into heavier elements is relatively minor perturbation to this one. So it's really cooking up of the helium in stars that matters. Observing helium abundance and subtracting the primordial one is actually very, very difficult, especially for old stellar populations. Instead of that, we can model chemical evolution of stellar populations and find that indeed there will be correlation between the amount of helium cooked up in stars, as opposed to primordial one, and the amount of heavier elements, which astronomers always call metals. That includes things like oxygen and carbon and so on. Now that is something that we can measure from spectroscopy. And so it turns out the typical metallicities of stellar populations today are of the order of solar, which is approximately 2% by mass, or maybe 1% by mass if you really account for all different stars. But it's of that order. And for each gram of heavier elements that's made, there are approximately 5 grams of helium that are made. The actual numbers are a little iffy and depend on exact models of stellar population evolution, but they're of that order of magnitude. And so we can estimate the net energy from star formation, or energy released by stars, by taking the mass of all stars formed times c squared times the efficiency of thermonuclear reactions, which is 0.1%, times the fraction of the hydrogen that was converted into the helium and heavier metals. And for typical numbers for galaxies today, that turns out to be an order of magnitude more than what we got from just release of the binding energy, of the order of 10 to the 60 ergs per galaxy, like a Milky Way. So it's really burning of young stars that will form the most important observable signature of young galaxies. And incidentally, active galactic nuclei, that's supermassive black holes that accrete material and convert some fraction of it into energy, can contribute comparable amounts as does all of the star formation. And right away that tells you that their energetics might be an important component in determining structure of galaxies and their star formation. So those are the generic expectations, and next we will take a look at the observational evidence for galaxy formation.